Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always, it's an honor and a privilege to be serving you today, as it is every day here in my virtual classroom. Step on inside for the Integrated Math 2 Big Ideas Math Folk. Here we are going to look at section 7.3, proving that a quadrilateral is a parallelogram. Now 7.2 was also about parallelograms, but they say if it's a parallelogram, here's what we do. We'll see what's different in the problems on these. I don't know. I know I've seen questions like them before, but it wasn't just with parallelograms at the time, the other ones. After this, I think we get to do a 7.1 to 7.3 review, but 7.4, I think, is on rectangles, rhombuses, and squares, and 7.5 is on trapezoids and kites. So we'll hit the other ones. They'll be a lot more bunched together. I don't know why parallelograms get two sections of something, and then rectangles, rhombuses, and squares all share one, and things like that. But yeah, we'll go and take a look at what's here. We're going to start with the lecture portion. Check out the description section below, so you can find timestamps to the problems that we do. This is the lecture portion here. But find the problem set here, find a PDF of what I'm going to navigate through with you right here. And we are going to be doing a problem set up to number 50. If questions start to look similar to the ones from before, a lot of them is once you set the thing up algebraically, you solve. I'm sure we're going to have to do things with graphs as well, but we'll take a look. Okay, so no new vocabulary. We're going to identify and verify parallelograms. So if you have enough information to determine it's a parallelogram, what is it? And show that a quadrilateral is a parallelogram in the coordinate plane. So we will be doing graph-based ones. Okay, given a parallelogram, you can use the parallelogram oh, by the way, I should just mention this right now. It's best that you know the stuff in 7.2 or that you've seen my stuff in 7.2 before we move on here, because they're already bringing up a theorem from 7.2. So just keep that in mind right now. Given a parallelogram, you can use the parallelogram opposite sides theorem and the parallelogram opposite angles theorem to prove statements about the sides and angles of the parallelogram. Very true. The converses of them are stated below. You can use these and other theorems in this lesson to prove a quadrilateral with certain properties as a parallelogram. Okay, so if an object is a parallelogram, then if a quadrilateral is a parallelogram, then opposite sides are congruent. The converse states, if in a quadrilateral both sets of opposite sides are congruent, then it is a parallelogram. This can be proven. I assume it looks like down below they're going to prove it. We'll take a look at that. The same is true of the opposite angles. If the opposite angles are congruent in a quadrilateral, then that quadrilateral is a parallelogram. Now, a lot of this stuff, I mean, we can look at the proofs. A lot of this stuff you can probably make sense of for yourself. Like, I can try and ask you, try and make something that's not a parallelogram. That doesn't mean therefore it is, but once you start to recognize what the affixed method things of, well, if these have to be the same and these have to be the same, I can't move it in such a way to make it not a parallelogram, otherwise it shortens that side, but they have to be that side. So it's one of those things where you could almost make sense of that fact, but it's nice to know that those first two, opposite sides congruent, opposite angles congruent, have converses as well. Remember, a parallelogram's definition is opposite sides parallel, just so you know. Okay, so they have those. Here's a proof for this guy. It's all CPCTC business. What do I mean by that? I mean, if you know that opposite sides are congruent here, they're going to show that this side's congruent to itself by the reflexive property. Now these two sets of triangles are congruent by CPCTC. Those two triangles are congruent by side, side, side. And then by CPCTC, they go into the alternate interior angles route of things. So they say, all right, if these two angles are congruent because they're corresponding parts, then that means by the converse of the alternate interior angles theorem, those lines are parallel. And if these two angles here are congruent by the converse of the alternate interior angles theorem, then both of these two sides are parallel as well. So by definition of parallelogram, opposite sides parallel, you got it. Anyway, yeah, it's really good to know triangle proofs from there because it really builds into what those things are. Let's move forward. Looks like we're not proving the congruent one. I'm sure we're going to have to prove it then together in one of the problems. Identifying a parallelogram. An amusement park ride has... Sorry, I got a notification. An amusement park ride has a moving platform attached to 4 swinging arms. The platform swings back and forth higher and higher until it goes over the top and around in circular motion. So it's kind of like a wee, kind of like that. Swinging along that guy. In the diagram below, AD and BC, here and here, represent 2 of the swinging arms. They never call it a parallelogram. They just say diagram. And DC is parallel to the ground. Now, they did mention this. This is parallel to that guy down there. Explain why the moving platform AB is always parallel to the ground. They need a space right there. So they're going to tell you some stuff. Why does this always have to be parallel to the ground if this is? So the swinging arms, I don't know if they ever mentioned the swinging arms have to be parallel, but they must be congruent, right? Do they say that? Circular motion. Circular motion would mean always congruent. The shape of quadrilateral ABCD changes as moving platform swings around, but its side lengths do not change, right? They're going to stay as they are, and they're the same thing. Both pairs of opposite sides are congruent, so ABCD is a parallelogram by the opposite sides converse. So it's just working itself out. Same thing as the converse. Oh, they have numbers. I didn't see that. Opposite sides are equal, therefore, by that thing. I feel like I need to write these down. Parallelogram, opposite sides converse. If they ask me to explain what it is, I won't remember the name. So parallelogram, opposite sides converse. I'm going to keep this in like a copy-paste format or something like that. Parallelogram, opposite angles converse. Yeah, if they ask me to state that, I want to just have it ready just in case. So those are two of them. Okay. I don't know what I'm going to do with those, but there you go. See another example, finding side lengths of a parallelogram. So these are a lot like the previous problems. For what values is this a parallelogram? Basically go off the same things we did before. When they said it was a parallelogram, you set the opposite sides equal and solve for x, or whatever. Now here, they're doing the exact same thing, they're just asking a different way. In order for this to be parallelogram, these would have to be equal. So you still set them equal and solve. Now, this question is interesting because I should solve for the x first, then plug in x to figure out what y is. So they solve for x, setting these equal. They get 10. Then they substitute 10 in here to get 17. So y then has to be 17. So it's a system of equations, but you have to rely on the x to get the y. Okay, let's keep moving forward and let's look at two more theorems. The opposite sides parallel and congruent theorem. If a pair of opposite sides is parallel to each other and congruent to each other, then ABCD is a parallelogram. There's a proof showing up maybe at the bottom of this page. I'm not sure yet. And the parallelogram diagonals converse, the diagonals bisect each other, then it's indeed a parallelogram. So everything besides the consecutive angles supplementary thing, which should work, but it needs to be all the pairs. Besides the consecutive angles supplementary thing, the other properties of parallelograms all hold up. That opposite sides congruent, both pairs, means it's a parallelogram. Both pairs of opposite angles congruent means a parallelogram. And both diagonals bisecting each other means it's a parallelogram. The one that doesn't show up is the consecutive angles thing, and I feel like that would have to be true as well for a parallelogram. I can't see how it's not. Maybe they still haven't brought it up. The fifth one that we haven't mentioned, though, is this one. So this one's new. You get one pair of opposite sides, and that same pair are congruent and parallel. Then there's that. So that one's new. Opposite sides parallel and congruent theorem, diagonals converse. Okay. So this one's not a converse. This is like a new one. You could use, if they prove it, they're going to do a CPCTC thing there, obviously. Okay. Example 3, doorway shown as part of a building in England. Oh, that's weird. Over time, the building has leaned sideways. Explain how you know that SV equals TU. It's the parallelogram. Oh gosh, I already forgot what it's called. Opposite sides congruent and parallel theorem. That those are parallel and, oh, right here. Opposite sides parallel and congruent theorem. There's no parallelogram in it. Okay, so for that reason, we got to know the names. I wonder if they're going to ask us, can you tell if it's one yes or no? And if so, explain why. If they tell us it is, we just got to state a theorem. For what value of x is this a parallelogram? Same kind of thing as before. We have this diagonal bisecting this one, and in order for us to specifically know it's a parallelogram, this would then have to be congruent to that. This diagonal to bisect that. Set them equal, solve for x. And then they ask you, I guess they're double checking to make sure that those are both 12, but you solve for x, you get 4. Is that it? Nope, there's more. Let me move myself. Okay, so just more examples of the same. For what values of? So we're literally using the things that we did before, and we're just kind of answering. We're not answering in a different way. We're answering a different question. Because we don't know it's a parallelogram. Let's say for it to be one. All right, so here are those ones once more. This is just the old recap. Ways to prove it's a parallelogram. We got converses. Wait. Show both sides are parallel. That's the definition. And then some converses. We got converse 1, 2, 3 of the opposite sides, opposite angles, and diagonals bisect each other. There has to be the consecutive angles one. Yeah. Anyway, and then there's a new one. This is not a converse. This is actually opposite sides parallel and congruent for that one. Is that it? No. Oh, coordinate geometry. That's right. Show that it's a parallelogram. My guess here is we got to use one of those converse things. If I could show both sets of opposite sides congruent, great. If I can show that one opposite set of opposite sides is parallel and congruent, great. We're not going to be doing the congruent diagonals one, really. and the yeah, no, yeah, that's it. Or you can do opposite sides, all opposite sides parallel. So you can do anything with that. They go with the non-converse one. Same slope, same set of equal sides. And I might do that as well for the very reason that I can count rises and runs up to over 5. And at the same time, I can do 2 squared plus 5 squared equals beta squared. So I'm not going to use distance formula and midpoint formula. I'm going to be working more off those. And I'll just do that every time. I think it works out pretty well. Yeah, there's another example there. We'll do plenty of our own. Okay, great. Cool. So 10 minutes of that lecture. Let's go ahead and move into the vocabulary and core concept check and see what they have. A quadrilateral has 4 congruent sides. Is the quadrilateral a parallelogram? Justify your answer. Yes. There is something more specific called a rhombus, but yes, it is. As long as, because the pairs of opposite sides are congruent. It doesn't matter that they're all the same. However, it is more specifically known as a rhombus. Even though you're not, I don't know if you're supposed to know that yet. More specifically known as a rhombus. That does not mean it is not a parallelogram. Okay. Still a parallelogram. It's just there's a bigger, badder name for it. Which is different? Find both answers. Construct a quadrilateral with opposite sides congruent. Let's call this the A. That makes a parallelogram. Oh, it doesn't say how many pairs. This says 1 pair. Okay, I'm assuming this is both pairs. Construct a quadrilateral with 1 pair of parallel sides. I don't know that that's necessarily the same thing as the other. I'm going to mark that one a B. Let's see. Construct a quadrilateral with opposite angles congruent. That would make a parallelogram. A. 1 pair of opposite sides congruent and parallel. That's also an A. These 3 right here would all make you a parallelogram by their converse theorems or their other theorems. And this is just one that 1 pair of parallel sides, as we start digging into more things we're going to talk about later, it's known as a trapezoid. Parallelogram needs both sets of sides parallel. A trapezoid can only have 1 pair. Excuse me. Okay, guys, we're going to jump into the core of the problems. And like I said, if these things go quickly enough, we should feel pretty good. We're going 3 through 50. I know we're going to run into those kinds of problems that say, show that this would make it a parallelogram or what have you. So I think that'll go kind of fast because they're like the problems from before. I can say out loud what it is I'm putting in. So let's go and jump right into it. We're going to start with numbers 3 through 8. State which theorem you can use to show the quadrilateral is a parallelogram. Oh, I didn't put in congruent. Oh, I already forget the names. Let me paste it in here. Do I have it? Parallelogram, opposite angles. Okay. All right. So listen, they are on that side right there. So I'm going to leave the diagrams right there. You can see that we have congruent sets of angles by the markings and by the 100s. I'm going to type these as often as I can. Parallelogram, opposite angles, converse. All sets of those. And it sounds like they're all parallelograms, so we can just jump straight into them if they are. Number 4. 2 sets of 4s, 2 sets of 14s, 2 sets of 20s. They're opposite each other. These are indeed also going to be parallelograms by the parallelogram opposite sides converse. I'm going to be very cheap with you on this here, as long as my computer doesn't crash in the process of doing a bunch of copying and pasting. There's number 4. Number 5. This is literally all we're naming, huh? So number 5. This is a parallelogram by the parallelogram diagonals bisect each other converse. This one had a shorter name. Converse. Oh, I should look this thing up. Hold on. Diagonals bisecting each other converse. I think it was 3 words. Let me figure out what it was. Sorry about this. I'll remember after this. Parallelogram diagonals converse. Okay. Parallelogram diagonals converse. I'll type that. You'll get some ASMR during this one. For sure. Number 6, as it's all well drawn. Looks like a little copy paste we can do right here for number 6, right? So, listen. Saving myself some time. Yeah, number 7. So number 7 is not a converse theorem. This is the one that shows both. And you know what? It's good that we have these ones as practice. I'm going to remember the names more, I bet. This is the one where the angles are opposite each other. The sides opposite each other. One set are congruent and parallel. Only I forget what it's called. I forget if it starts with parallelogram, but I'll assume it does. Parallelogram, opposite sides parallel and congruent theorem. I feel like suddenly it doesn't start with the word parallelogram. Because the other ones are converse theorems, knowing that if it is a parallelogram, I'm just going to go ahead with that. Opposite sides parallel and congruent theorem. Sorry if the name's wrong, but the concept is right. This one's the same as the diagonal ones before. Parallelogram, diagonals, converse. 6, 6, and 4, 4. Those diagonals do bisect each other. And I got to give it up to the problem writers for this book, trying to find clever, cute, tricky ways to have you answer it by changing numbers and markings and stuff like that. It's kind of hard to do, and to devote 6 problem is true magistry. All right. In exercises 9 through 12, find the values of x and y that make the quadrilateral a parallelogram. So this goes kind of more into the realm of the same problems of the previous section. It's a parallelogram, solve for x and y. I mean, ish. X is going to be 114. Again, I'm not doing anything here if the problem's already copied down, unless there's work that I need to show, and I don't need to show any work here. In this particular case, y is x 114. And by the way, notice I didn't put degrees, because x already has a degree mark there. Why is x 114? Because it's an opposite angle with this thing here. And what we're building off of, notice that I didn't do, by the way, the supplementary one. I didn't say x minus 160 or 180 minus 66 is x and all that stuff, because they didn't seem to call that a theorem. But this is based off the parallelogram opposite angles converse. If the opposite angles are congruent, if x is 114 and if y is 66, opposite the other 66, it would make it a parallelogram. And I over-explained that problem. Number 10, we're going to use the parallelogram opposite sides converse. Opposite sides need to be congruent in order for these things to be what they are. So x would have to be 16 and y would have to be 9. Again, kind of just flies right in the face of kinds of problems that we have there. Numbers 11 and 12, same concept, figuring out what theorem it is, but we have to do a little bit more to solve. So on number 11, we once again you get to use the parallelogram, opposite sides converse. So we get to say that 4x plus 6 equals 7x minus 3. Solve for x, subtract 4x from both sides, add 3 to both sides, divide both sides by 3, you get x equals 3. I think they only ask for x and y. They're not asking for like the missing lengths there. For y, once again, parallelogram opposite sides converse, set these guys equal. Subtract 3y from both sides, add 3 to both sides, you get y equals 4. So those are those two values. And then number 12, we're going to once again use the parallelogram opposite angles converse. This one's a little bit different because there is a y tucked in here where all the other ones are x. So we almost, in a way, have a system of equations. But let's go and start with the ones where we can just find x to begin with first. Set these two equal. If we set those two equal with the other two set equal, those x's would give you, and y's would give you a parallelogram. So subtract 4x from both sides, add 12 to both sides. You get x equals 25. Now, in order to find y, we're going to begin with that 4x. Oh, whoops, I already wrote that. We're going to begin with the 3x minus 8 equals 4y plus 7. However, now I get to substitute 25 in for x. Like that. Yikes. So 75 minus 8, 67. Subtract 7, divide by 4. So I'm going to get y equals 15. A little more work to get there algebraically, but we're there. Okay, going through quite swiftly. Of course, we do know it's going to slow us down later. They're starting us nice. Number 13 through 16. Find the value of x that makes a quadrilateral parallelogram. More of the same. I'm glad they don't say justify which theorem. I think we spent numbers 3 through 8 doing that. So, but I'm saying them out loud. This is the parallelogram diagonals converse. Here, they have to bisect each other. So this one is bisected by this guy. Now this guy has to be bisected by that guy, which means this has to equal this. I need 4x plus 2 to equal 5x minus 6. 4x plus 2 equals 5x minus 6. Subtract 4x from both sides, so you get x. Add 6 to both sides, you get 8. Come on, give me a challenge. Number 14 is the non-converse theorem, parallel opposite sides, parallel incongruent theorem, I believe it's called. I got to see if it actually literally does have the word parallelogram in it. But same thing. These sides are parallel. In order for this to truly work the way that it is, I need 2x plus 3 and x plus 7 to equal the same thing, which means I need to find out what value of x works. Subtract x, subtract 3. This has been my favorite assignment so far. It's been quick. Number 15, same theorem as number 14. And number 16 looks to be the same theorem as number 13. But number 15 here, I need 3x plus 5. What I am curious about, we haven't had like any fraction answers, any quadratics. You know, they're really just going straight into it, not find the length of afterward, just what value of x. Pretty straightforward. Sorry I talked right through that problem with the algebra. Number 16, same bit as before with diagonals, parallelogram diagonals converse. 6x and 3x plus 2 are going to have to be the same thing for this to work out. Whoops. Equals. They're going to have to be the same thing for this to work out, because if they ain't, then the diagonals don't bisect each other, and therefore it's not a parallelogram. Let's keep this stuff in mind as I just say, oh, here's a fraction. As I'm saying what I just said right there. We know that if parallelograms, if the quadrilateral's diagonals bisect each other, it's a parallelogram. Must they? Yeah, that's one of the parallelogram's properties. A parallelogram's diagonals bisect each other. So if these things aren't true, it is not. It is absolutely not a parallelogram. It will not be. So they have to be true for it. Which, find the value that makes this a parallelogram. It doesn't if it's not. All right, 17 through 20, graph the quadrilateral with the given vertices in a coordinate plane, then show the quadrilateral as a parallelogram. I think I can do this plenty fast compared to that of what the book's lecture stuff would have done. Because what we get to do here, the only problem is I got to plot them and label them. So A, I'll say it in a moment, but A, B, C, oh, B is, C is going to be out here, sorry. So I'm guessing D is down here, yeah, 8-1. What I'm going to do here is kind of kill two birds with one stone. I'm going to find, I was about to say the midpoint. I'm going to find the distance between two sides at the same time. Oh, this one's really easy, actually, this particular problem. But even other ones. I'm going to find the distance with nearly the same amount of energy as I would find the slopes for problems. Now, this one's significantly easier than others because I can use this segment and this segment right here. My only goal, and you do not have to use this version of a thing. You can either do find out all of them have the same, or two pairs of opposite sides are parallel. You can find all four, two pairs of opposite sides congruent, or you can find that one pair of opposite sides is both parallel and congruent. And that's the one that I think we generally want to do. If I just use AD and BC, the slope of AD is 0. Flat line. I don't have to calculate anything for this. The slope of BC is 0. What I have to do is see if they have the same length. This one can literally be counted and you're done. 1, 2, to 8, right? 0 to 8. And this goes from 4 to 12. So 1, 2, 3, 4, 5, 6, 7, 8. So 4 to 12 there. So length of AD is 8. Length of BC is 8. This is therefore a parallelogram. Same slope, same length for the same segments, opposite each other. Show that it is. Same slope and same lengths for opposite sides. I'll fix that H. So therefore it is. Yes, it's a parallelogram. So I think that's going to be the same for the other ones. Now this one had flat lines. I think I made it very easy. Flat lines. Horizontal lines. That was pretty nice. All right, number 18. I kind of slowed down then. Okay, E, F, G, H. Oh, they get to use different letters each time. All right, -3, 0. -3, 4. Well, there's vertical lines. This one maybe gets to be just as easy. 3, -1. And 3, -5. Is EFGH a parallelogram, and why? So this one, again, on the same level probably as the previous one. Let's look at the vertical lines. Vertical lines have the same slope. Now, a slope of a vertical line is undefined. E, F, G, H. But undefined together, vertical lines will mean they are parallel. So, Why is EF parallel to GH? Because the slope of segment EF is undefined and the slope of segment GH is undefined. Now their lengths are also the same. EF has a length of 1, 2, 3, 4. GH has a length of 1, 2, 3, 4. Both parallel, both congruent for opposite sides, and the same set. It is a parallelogram. I don't know if I have to write, therefore, it is a parallelogram. It would be the same each time. They're telling us, show that it is. They're not tricking us. It is. We just got to kind of work it out. Two more, number 19. Let's do some diagonal ones, shall we? Negative 2, 3. I'm going to assume this one is. Negative 2, 3. Negative 5, 7. 3, 6. 6, 2. Okay. Purely diagonalness. So let's pick a set of sides opposite each other, one or the other, and let's work out the magic that they want us to work out here. So this is JKLM. Let's work with KJ and LM. I think we can just talk about them. So here's what I'm going to do. I'm going to count this kind of like slope right there. And guess what? We're going to have to work off this same thing right here. I'm drawing them kind of in different parts so you can just see where they are. So from K to J, this goes down 1, 2, 3, 4, and right 1, 2, 3. This goes right. Oh, 1, 2, 3, 4. Did I plot something wrong? That's a 7. Let me fix that. Show it's a parallelogram. That's not a parallelogram. There we go. All right, pretend like I did that. Okay. So this goes, there we go. This goes right 1, 2, 3, and down 1, 2, 3, 4. So 3 and negative 4 like that. So the slopes of them, it's not, do you write the right on top and then down? No, it's rise over run. So you always do it kind of that direction. So the slope of segment KJ, JK, probably should have put JK, of KJ is negative 4/3. And the slope of segment LM is also negative 4/3. Now, what did this also allow me to do? I have to find the distance from here to here, from here to here. These are right triangles. That's a right triangle right here. I'm going to use Pythagorean theorem. This squared plus this squared equals that squared. I'm sure we've done some of these together. This squared plus this squared is that squared. Can't guarantee that we have, though, because we probably spent more time using the slope parts to do find midpoints, and also I think slopes. I don't think we were using it for Pythagorean theorem, but this is a whole KJ. KJ is this length right here. We have a squared plus b squared equals c squared. That length. So we got to find KJ from that. So that's 16 plus 9 is KJ squared. And I'll be honest, I wonder if it's enough to say that, look, these are the same things, negative 4 and 3 and negative 4 and 3. Is that enough, or do I actually have to find the length itself? I guess I'll find the length, but it's not actually a requirement. Anyway, if you take the square root of both sides, you get KJ is 5. That is the length of KJ. The reason I bring that up is because LM is going to have the same things. Literally, Pythagorean theorem, I can reverse the numbers all I want, 3 squared plus negative 4 squared, but the fact of the matter is the same numbers. That's where this can almost feel a little redundant when you get the drawings, when you have the drawings and use them. So 9 plus 16 is LM squared. Whew, this problem's taken a while in comparison. And LM is also 5. So we're just getting to the idea, same slope, same distance, therefore by the theorem, yes, it's parallelogram, by the opposite sides congruent and parallel theorem. Of course, I could have also found the slopes of the other parts. Yeah, totally. Number 20. Maybe I'll do that for this one. Maybe we won't find distances. We only use slopes, you know? Because opposite sides parallel will totally work. Negative 5, 0 is N. 0, 4 is P. 3, 0 is Q. Negative 2, negative 4 is R. Okay. Let's find some slopes, shall we? This time let's actually draw them the same direction so you're not confused on it. From N to P. It's a rise of 4. It's a run of 5. From R to Q, it's a rise of 4. It's a run of 5. Now check this out. So what if I did this instead? Let's go from P to Q, 1, 2, 3, down 4. And from N to R, 1, 2, 3, and down 4. Oh, that kind of gets in the way. But those are the slopes here. So I could have always gone for it this way every time as well. So the slope of NP, segment NP, is 5/4, and so is the slope of segment RQ. Positive 5/4. Meanwhile, so same. Meanwhile, the slope of segment PQ is negative 4/3, and so is the slope of NR. Slope of segment NR is negative 4/3. This is the definition of a parallelogram. I don't know if they say the converse of a definition. This is the definition. Both pairs of opposite sides parallel. Could have I done that for any of the problems? Yeah. I think the first two are, needless to say, without it, you don't need them. This next one is good to kind of embellish and show those things, how the slope, the concept of it, can also get you distances. But that also works. If you're curious on distances, this length would be root 41. Root 41, and this length is 5 and 5, like it was last time. Okay, I'm going to go ahead and move forward. Let's see what happens next. We got some error analysis. I think generally after error analysis is where we start hitting more of the word problems. We're not halfway done. We should start feeling like we got to do more things then. In exercises 21 and 22, describe and correct the error in identifying a parallelogram. I see where they're at with this. Take a look at that diagram. They say it's a parallelogram by the parallelogram opposite sides converse. See, they always say correct it. There's no way for me to show it's a parallelogram because it's not. This is known as a kite. However, they are incorrect because it is not opposite sides that are congruent, but rather consecutive sides that are congruent, like a kite. Which, once again, maybe not a word that you know yet, and that's okay. But yeah, if the lengths were different, if the 5s were opposite each other and 7s were opposite each other, we could do that. So I don't really know how to correct it other than say that they're not parallel. It's not a parallelogram. So, correction. So, like a kite, but not a parallelogram. Okay. That's my correction. All right, number 22. I got a 13 and 13. This is parallelogram by the opposite sides in parallel congruent theorem. Well, I only see opposite sides congruent. I don't see any parallel. Those 13s are well on their way to say it could be a parallelogram. There's no must be in sight here. They only have opposite sides congruent, which is not enough information to conclude that it is a parallelogram. However, if those opposite sides were parallel as well, then by their stated theorem, it would be a parallelogram. Okay. So given that, we needed these to be if JM, if opposite sides were parallel as well, I'm talking about JM parallel to KL. If they were, then we'd be where we want to be. All right, number 23. What value of x makes the quadrilateral parallelogram? Explain how you found your answer. Very interestingly, there are a bunch of different sets of x that we could choose from. Does it matter which one we use? Does it give us the same answer no matter what? I'm really curious to try this out. What value of x makes the parallelogram? Explain how you found the answer. Let's start with the side bits and let's just experiment with all these and see what happens. Let's try the top and bottom. If 3x plus 10 equaled 5x, I'm going to subtract 3x from both sides and divide both sides by 2. I get 5. Let's see if this keeps going. If I had 3x plus 1 equals 4x minus 4, I could subtract 3x from both sides, add 4 to both sides, I still get 5. Okay. So either of these could be using the parallelogram opposite sides converse. So they said explain the reason. By the parallelogram opposite sides converse. On the other hand, if we use the parallelogram diagonals converse, we could then try and set those diagonal bits equal to each other, and we could say that 2x plus 1 would have to equal x plus 6. Subtract x from both sides, subtract 1 from both sides, you still get 5. And try the 4x minus 2 and 3x plus 3. Subtract 3x from both sides, add 2 to both sides, you get x equals 5. This is the parallelogram diagonals converse. We still get that x. Basically, the answer is x equals 5. You're just using other ways to assure yourself of it, but they said which ones, what value of x makes them a parallelogram. All these things would have to be true. I just don't think you need to solve all of them. Once you solved one of them, if they set up the problem the way it did, then it's going to work out. If they didn't, then it would never be a parallelogram in the first place. So I feel like you can just do one and then you're good. As long as you set the right ones. You know what part of the thing that throws you off is, which one do I set it equal to? 3x plus 10 has to be with 5x and things like that. All right, making an argument. Your friend says you can show the quadrilateral WXYZ is a parallelogram by using the consecutive interior angles converse and the opposite sides parallel incongruent theorem. Is your friend correct? Explain your reasoning. So this brings me a little halfway to my argument. I was thinking you could, they called them consecutive interior angles. That makes sense for the theorem. But I'm thinking on the same side interior angles, if these are supplementary, if these are supplementary, if these are, then great. But they're doing a different method. They're saying, what if I use these guys here congruent and said, supplementary, which is the converse, and then said these sides were congruent here, would that be enough information? You could. I'm trying to read on this part why they have this here, because we don't know these opposite sides are parallel. We will be able to prove it, but you don't need to. Oh, yeah, I guess you do. Okay, I take back. Okay, so here's what I'm getting at. Consecutive angles are supplementary. By the converse, by the consecutive interior angles converse, this is like a same side interior angles thing. If these two are supplementary, two lines cut by a transversal, these two lines are parallel. They are parallel, and that's what we're trying to say. Makes these two lines parallel here. Yes, because now you have the same set of opposite sides parallel and congruent, and that would work. So yes, your friend is correct. The consecutive angles that are parallel, the consecutive angles that are supplementary means their respective lines are parallel, and those lines, WX and ZY, are also congruent to each other. I shouldn't say lines, I should say sides, but that's okay. Therefore, by their last theorem, it is. Therefore, by the opposite side or opposite sides parallel, congruent theorem, WXYZ is a parallelogram. Okay. All right. Here we go. Let's keep moving forward. Numbers 25 to 27, write the indicated theorems as a biconditional statement. 25. The theorem and its converse. Does biconditional... I know what biconditional means. I'm trying to think if... I think I need to use the word if and only if to make it biconditional. So a biconditional statement means that a statement, theorem, and its converse are also true. Not just theorems, but just anything in life. If they're true. These ones do have them that are true. So a parallelogram, a quadrilateral is a parallelogram if and only if, I mean, this is using the very specific ones, the opposite sides theorem and its converse, if and only if both pairs of opposite sides are congruent. Okay. I'm realizing my chair slowly sinks over time. This started within the last couple weeks, but it's really apparent now. So I apologize if you keep seeing me do that. I believe the if and only if is the thing that makes this thing true. That's what I'm aware of when it comes to this the saying. If and only if means it only qualifies in this statement. That means if I flip it, it would also make the other part work. So the if and only if guy. That's what I'm making it as a biconditional statement. Okay, so you're gonna say the if and only if part every time. So number 26, the parallelogram opposite angles and converse angles theorem. Let's kind of work the magic of copy paste. Quadrilateral is a parallelogram if and only if both pairs of opposite angles are congruent. Now it needs to be both. It needs to be both, and then it's going to work itself out. So these are the three converses, like I said, that we'll be working together. And number 27, if and only if the diagonals bisect each other. A quadrilateral is a parallelogram if and only if it's both pairs of diagonals bisect each other. Remember, it's not about the diagonals being congruent. They create congruency within themselves, each other. The diagonals aren't congruent. That'll be true for rectangles and squares and things like that, but not for parallelograms. Okay, number 28. Describe a method that uses the opposite sides parallel and congruent theorem to construct a parallelogram, then construct a parallelogram using your method. Describe a parallelogram that uses the opposite sides parallel and congruent theorem. That uses the theorem? Describe a method. I'm going to do the thing. I don't know what they mean by describe. I'll say it out loud and see if I can type something out after that. So here's what we'll do. We will make a side of a length like that. Boom. To make it even harder to kind of construct here because you guys won't know what a straight horizontal line is. I'll go ahead and do that. I can also then construct some other line thing after that, right? These can be two parts of a parallelogram. Now my goal is to make another side that is the same length as this and parallel to it. So my thing, see, I already feel myself sinking right now. Literally, I sank a lot. There's something that's going on with my chair. Anyway, significantly more than the last time. So let me get my tool. Where'd you come from? Hello. All right, so I'm gonna get my tool here, and I want to make a side length that's the same length as this one. And I can do this a bunch of different ways. I can even make the arc to begin with as long as I get that same length the same. So let's do this. I don't know if I can make it exactly the same length. This has one of those snappy features. It kind of snaps in and out kind of hard. So let's see if this will work. Sorry about this. This is the part that'll definitely slow me down. Okay, not bad. Yeah, that'll be fine. Okay, so I have this length right here, right? That itself doesn't matter, just the fact that I have that width. I can keep that width, and from here, I can make... Generally, I do the arc afterward, but I'll just make it now, just to say something's got to be along this length right here, but it's got to be parallel to this other one. So the only thing I did with an arc there is I just know that the next line I draw has to go out to that amount. So I'm going to work on copying this angle right here. That's the goal. And in order to... Oh, that's why I have to do that last. Let me draw a dot right here because I'm going to extend this line out. Okay. This is where I'm going to draw it from, right? So I'm going to copy this angle right here by drawing the same arc down here. And then I need to get this width of this guy. Find out how wide this guy is right here, because however wide that is where these two parts intersect. And again, this snap will not be perfect. See, that's too far out. And this ain't far enough. Oh, look at that. This thing changed a little bit. Dang. Maybe I do need to snap it out. There we go. All right, that'll work out. So whatever that is right there, I need to do the same thing right here. And when I draw that, where that thing intersects is where I need to draw my line through from this guy. I need to draw it through there and to that end, through that, to this arc, boom, like that. There, boom. Now those are parallel and congruent to each other. I mean, as much as I can construct myself. So these are parallel. These are also congruent to each other. And then I can connect the last set of sides. Okay, there's my parallelogram. So using that theorem, I went about that. So I copied, I'm syncing again. Oh no. That is significant too. That's not even close to like, it's not tiny. You probably see me going way low in my thing. That was in the same problem that I kept syncing. So yeah, how do I describe that? I don't know how to say describe it. I'll shrink it to that now, by the way. But yeah, I drew a segment. Let me just lower this a little bit. Draw. Come on. Draw a segment of a desired length and angle another line or side off of it. Find so when I copy the angle for the converse of the corresponding angles theorem to make parallel lines via the converse of the corresponding angles theorem. Then, which I did the side length thing after, determine the side length, the length of the original side, and copy it with the side. Okay, so that's what I did there. Then connect the final two sides. Okay, so connect the final, not the final two sides, but the two that are not yet connected. Okay, so that's what I did there. Okay, that is number 28. Stop syncing. I need to figure this thing out. Okay, let me pause this for a second. Something's wrong with my chair. Okay, and I didn't fix the chair issue, but I can't say for certain that I'll know what to do to fix it. So there's that. Okay, did we just do 28? Was that the last? Shoot. Yeah, 28. Okay, number 29. Follow the steps below to construct a parallelogram. Explain why this method works. State a theorem to support your answer. Well, I know the theorem I'm going to state. It's the diagonals, parallelogram, diagonals, converse. But let's see what they got. Whoa, not red. All right, use a ruler. Oh, follow the steps. Use a ruler to draw two segments that intersect at their midpoints. Connect the same. Well, this isn't a true construction, as in it's not compass construction, but it's the thing. So follow it. Okay, I'm gonna get a ruler. I don't know how to rotate. There we go. Let's measure something at. Can this go right on the line? No. Let's measure something at 6 centimeters. I'll seek its midpoint at the 3 centimeter mark. Right there. It's not really drawing, but I got a little piece of it. A lot piece of it. And then let's do another one. Let's do it 4 centimeters long and do it at the 2 centimeter mark, like that. Think that'll work? Oh. Of course, it's snapping out of place for me. Just do the best I can. I feel myself sinking. So there's the 2 centimeter mark. Boom, right there. Now I just got to connect those things up. So I know that this is congruent to this, and I know that this is congruent to this. So this is the converse of the diagonals theorem. The parallelogram diagonals converse, I should say. And boom, we made a parallelogram. I mean, that's a pretty fast way to be able to do that without needing any parallel stuff. Are you serious? Without needing any parallel stuff along the way. So what do they want? Explain why the method works. State a theorem to support your answer. It works because of the theorem that it is. This makes a parallelogram because these diagonals are bisecting each other. And by the parallelogram, diagonals converse, this would then be a parallelogram. I already said that. Oh, I probably didn't need to say that last part, but just that's the thing that it is. Is this all construction moving forward? Number 30. Your brother says to show that quadrilaterals are parallelogram, you must show that these things are parallel. QR and TS, QT and RS. Your sister says you must show QR is congruent to TS and QT is congruent to RS. Who is correct? Explain your reasoning. They're both correct. So there's more than one thing you can use. I even demonstrated that. I didn't do all the sides congruent, but your brother, which I don't have one, but your brother is correct. And I have two sisters, but my sister says correct. Both my brother and sister are correct. My brother indicated, well, they're both wrong if they said that that's the only way to show it. You know what I'm convinced with? I have a little thing underneath my carpet thing that kind of broke. And so maybe if it's not level, then it can't stay upright. My brother indicated that opposite parallel side. My brother indicated the definition of a parallelogram would show that it is. And my sister used the parallelogram opposite sides converse to show that it's a parallelogram. There's also the one that we've been kind of doing more so, the one parallelogram opposite sides congruent and parallel theorem, and that one showed it as well. All right, number 31, in exercises 31 and 32, your classmate incorrectly claims that the marked information can be used to show the figures of parallelogram. Draw a quadrilateral with the same marked properties, clearly not a parallelogram. See, I like these kinds of questions here. It goes to show how you can disprove by counterexample in ways that wouldn't work. You can't disprove the ones we've used by counterexample yet. What they're showing is just by vertical angles alone, would that make... Could you will it absolutely always be a parallelogram? And that's what they're showing you. They're saying if vertical angles are congruent for the diagonals, then it's a parallelogram. Newsflash, all diagonals will always make vertical angles when they intersect. Always. And vertical angles are always congruent. So no, that's not going to do it. Here, let's upset that by this. Let's just draw two lines like that. Boom. Is this going to be a parallelogram? Heck nah. Is this thing here? Are these two sides right there parallel here and here? Nuh-uh. Nuh-uh. Maybe these two are. I have no idea, but those two sure aren't. This is not a parallelogram just because vertical angles are congruent, which, by the way, they always are. So, yeah, no. Clearly, it is not. I could make it even more clearly, but I'm good. Number 32. Number 32, so this one's a little more specific and important because we have used the parallel lines thing with the congruent sides, but they have to be for the same sides. Opposite sides parallel and congruent, one pair of them. This is one pair of opposite sides parallel, one set of parallel sides congruent, but they're not the same ones. So what if I did this? This is parallel to this, right? And then these are both 8. I could make a trapezoid. I'm sure there are probably other things I could do, but this is 8 and this is 8 and these two are parallel. That's a trapezoid now. These aren't parallel, so it's not a parallelogram, even though those two sets are congruent. So I like those kinds of questions. It really does dispute that concept of what it could be and things like that. Okay, I'm really something with this chair. Ever since I spoke it into existence, it's been lowering super fast, and I apologize. Number 33, modeling with mathematics. You shoot a pool ball and it rolls back to where it started. I think I've done that before. As shown in the diagram. The ball bounces off each wall at the same angle where it hits the wall. The ball hits the first wall at an angle of 63 degrees. If that's not marked, I'm going to do that. What's first wall? Measure of angle AE. Where's A? Oh, there's A. AEF and B is equal to BEH at 63 degrees. So this is the 63. It's saying it hits the wall. That's not what I thought they meant. BEH is 63 degrees each. This is just part A. What is measure of angle AFE? Explain your reasoning. I'm not saying... I don't know what this has to do with the parallelogram yet. But on the first one, part A, so those parts are 63. Measure of angle... The measure of angle AFE is going to be 90 minus 63. So here's the thing. It says explain your reasoning. These are complementary angles together. So 27 degrees. Pool table. I still don't know what this has to do with parallelograms yet. I mean, it's going to indicate itself by the opposite angles congruent thing. I get it. And other questions there. But we're not explaining anything by parallelograms, converse, anything like that. It's going to be 27 degrees. This is a right angle right here. Right triangle. So the two non-right angles are complementary to each other. The two non-right angles in a right triangle are complementary. So there's part A. I feel myself sinking. Part B. I want to see on my camera. Am I sinking clearly? Okay. The top of my head's right there. When I finish this problem, we'll see where I am. Part B. Explain why measure of angle FGD is 63 degrees. FGD. Where's D? Oh, there it is. 63 degrees. See, there's a parallelogram. This can kind of get more to parallelogram concept. Why is that 63 degrees? Because, well, do I want to say something very specific here? No. Because... measure of angle FGD is 63 degrees because opposite angles in a parallelogram are congruent. And listen, the other thing that we're not really talking about is this diagram, this pool table. The pool table, I should have mentioned, I think I kind of did with the right triangle thing, the ABCD, it's a rectangle. So a rectangle is also a parallelogram. I think that that's important to note. And it is around another parallelogram, rectangle. I'm probably not giving the best definitions. It's around a rectangle. We don't know which are rectangles yet. That will have congruent sides. Angles outside, congruent angles outside those opposite angles. That doesn't really work well. Basically, because G and E are so samey. G is like E as far as angle measure. We haven't found its angle measure yet, but they're the same. Therefore, the ones outside of them will be the same with the way that this rectangle is constructed there. All right, part C. Part C, we have what is measure of angle GHC? GHC is this guy. You cannot see that at all. GHC is this guy. And EHB, well, whatever they are, they're going to be the same for that kind of same reason here. I should have mentioned, so this was 27 degrees. They don't ask me why. If this is 27 degrees, then those are going to be 27 degrees. Measure of angle GHC is going to be the same as the measure of angle EHB, which is 27 degrees, same as that AFE, or whatever they called it, EFA. And part D is quadrilateral EFGH a parallelogram? Explain your reasoning. Oh, I thought they first said that it was. Shoot, I have to answer part B differently. I thought they said it was a parallelogram. Hold on. You shoot a pool and it rolls back to where it started shown the diagram. Oh, ball bounces off the wall at the same angle which it hit the wall. Bounces off the wall, same angle which it hits the wall. I don't know if my reasoning works. My reasoning doesn't work for B because we don't know it's a parallelogram yet. I've totally sunk. Oh my gosh, I am so low down. This is bad. Okay, I'm gonna look this up later and just kind of figure it out. This literally, I'm willing this thing into existence in the worst way. This is not good. B. What do I want to say for B instead of this thing here? Let's see. What problem is this? 33. So 33. Whoops. I just lost my page. So 33, 63, 63. I mean, I want to talk about the outside. about it being a rectangle, so it bounces off that way. It goes back to where it started. They show their congruent angles. I don't know if that's enough to kind of work it out and just say like, yeah, that's pretty good. You know, because we haven't talked about rectangles yet, so it's kind of How about this? This they show congruent marks. Maybe we can just say that. Because they share the same congruent marks as opposite the pool table. I don't know. I didn't get a good answer to that one, so I feel bad. So in part D, is it a parallelogram? Explain your reasoning. So here are some measures we can now find out. How about this? Let's just find out what the measures inside are now. I think this will work out. 63 plus 63, or 63 times 2, is 126. And 180 minus 126 is 54. So measure of angle E, if you will, HEF, measure of angle HEF equals the same as the measure of angle HGF, which is 54 degrees. Those are opposite angles that are congruent. The other guys that are 27. 27 times 2 is 54. And, oh, check that out. 180 minus 54 is 126. And measure of angle EHG. I really slowed down on these problems. Is the same as measure of angle EFG, which is 54 degrees. So we got, 126 degrees. So not only are opposite angles congruent, but it also shows that these guys are supplementary, 54 and 126. So that also works out in its own way. So yes, because of the opposite, because the parallelogram, opposite angles converse. It's a parallelogram because of that. Okay, let's move forward. Number 34. In the diagram of the parking lot shown, measure of angle JKL is 60 degrees. JKL is 60. JK and LM are 21 feet. JK, 21. LM, 21. KL and JM are 9 feet. That's the 21. KL and JM are 9. Explain how you know how to show it's a parallelogram. So on number 34A, it's a parallelogram by the parallelogram. So they're each opposite 9s and 21s. So by the parallelogram opposite sides theorem, or converse, JKLM is a parallelogram. Okay. B, find the measure of JML. JML is right here. That's going to be 60 degrees because it's opposite that angle. Measure of KJM, boom, and measure of KLM. Okay, so we're just finding all the parts within the parallelogram. They don't say why, we'll just go after it. Measure of angle JML is going to be the same as measure of angle JKL, which is going to be 60 degrees. Measure of angle KJM is going to be the same as measure of angle KLM. Both of those are going to be 180 minus 60, which is 120 degrees. So boom, boom. Part C, LM is parallel to NO. LM is parallel to NO. And NO is parallel to PQ, Which theorem could you use to show that JK is parallel to PQ? Where's JK? JK parallel to PQ? I don't remember what it's called. It's the parallel... two lines parallel to the same line are parallel to each other. It's not called the transitive property. I'm gonna look up what's called. Two lines parallel to a third line are parallel to each other theorem. Two lines parallel to I don't know what the name of the theorem is, but it's just a theorem that states that two lines parallel to a third line are parallel to each other, or to the same line, or whatever, something like that. Maybe it is called transitive property. I was thinking it's not transitive property of congruence. I think that makes sense because it has that same thing. So I'm going to call that transitive property of parallel lines. I mean, it can be proven. I just don't know if that's the name of it. If it's a property or if it's a theorem. I'll go with it. All right, number 35. Now, two lines perpendicular to the same line aren't perpendicular to each other. That don't have no transitive property. You can't do that. All right, number 35. Whoops. Describe how to prove that ABCD is a parallelogram here. It doesn't say prove it. I wonder if I can go without it or what. Next, probably not. It just says describe how to prove. All right. So on the first one here, number 35, basically you have some givens. Describe how to prove. I don't know if I got to use a proof or not. I'm going to say no. It says describe it. So you are given AD congruent to BC. I'm just going to say that. And angle ADB is congruent to angle CBD by the reflexive property. You can say that BD is equal to DB, just shared parts, and the triangles are equal by... Oh, I'm stating too much. I don't have to prove congruent triangles. Sorry, I take all this back. I just need to show that these two sides are parallel. I forgot what I was looking for. So you're given that those two things are equal by the converse of the alternate interior angles theorem. AD is also perpendicular to BC. Now I'm missing some of the segment bars and things like that. I'm sure you have to go with that. So by the opposite sides parallel and congruent theorem, ABCD is a parallelogram. I feel like my video content is significantly worsening because I can't come up with things the best way I want to say it. All right, that's number 35. Number 36. Plus my chair keeps lowering. We'll just go straight off the parallel lines. Or straight off making parallel lines from these things here. Alternate by the converse of the alternate interior angles theorem, AB is parallel to DC and AD is parallel to BC for both sets of given congruent alternate interior angles. I'm just going to state what they are, right? You have the markings that are marked there, and that means that you can use those things here. So because of these two angles being congruent, this guy here and this guy here, we can state that these two lines are parallel, or sides. And because this one is congruent to this one here, those are two lines cut by a transversal right here, these also are going to be parallel as well. By the definition of a parallelogram, ABCD is a parallelogram. This is by definition. You have two sets of parallel sides. By its very definition, ABCD is a parallelogram. Okay, and then number 37. Number 37, we have technically alternate interior angles right here as well. Alternate interior. Those are congruent to each other, so boom, those are parallel. These are opposite angles congruent. I'm trying to decide if I can say something about supplementary to that linear pair and a linear pair because the parallel lines. I'm wondering if there's a faster way, basically, for me to say it than that. That's a lot for me to say. So, yeah, let's go off the alternate. Yeah, let's go off of that. So, okay. This time I have to kind of say some letters here. So, angle B is going to be, because angle B is congruent to angle B. Oh, but they don't give any letters. C. Shoot. Shoot. I'm trying to think if there's a way I can state that this is what it is without saying the lines are parallel first, and I don't know if there is. Oh, I have corresponding angles here, but I just can't call this something without giving another letter on it, that's all. Corresponding angles would make those lines parallel. Oh, you know what? Okay, hold on. Okay, then I don't have to set these things up. I'll just state that there is a pair of alternate interior angles that make... So, the converse of the AIA theorem states that AB would be parallel to DC, and the converse of the corresponding angles theorem states that then AD is parallel to BC. So that's the part I didn't mark up here. So we could do this. These two alternate interior angles here would show these lines are parallel, and these two congruent corresponding angles here would show these two lines are parallel. So we can do it that way. So we don't have to get those other sets of angles. By the definition, ABCD is a parallelogram. I'm sinking in my chair. Okay, number 37. All right, number 38. Quadrilateral J. I feel like this is where the problems are going to get long. Oh, proving a theorem. 3 different proofs in a row, and I still have this one. Quadrilateral JKLM is a parallelogram. Describe how to prove that triangle MGJ is congruent to triangle KJL. Okay. All right, so, sorry. Okay, so let's work off this. So we got a parallelogram. So parallelogram would automatically have opposite sides parallel. We have that. Can I work that to do anything with the angles? Yeah. I'm not going to go with the angles yet. Parallelogram would then be able to use opposite sides parallel, or congruent, I should say. So that means I can make that congruent to that. What I want to look at is how I can state that either due to parallel lines or some sort of... let's see, that doesn't work. So these are congruent from that. Can I say that's congruent to that for any reason? Not off the bat, no. I could instead do... Sorry, let me get off this. Or let me figure this thing out. Right angle there. I wonder if I should do some sort of extension thing with this thing and make it work out and say that... I'm wondering if I'm going to do HL or angle side for this one. That's kind of what I'm looking at. I really want to work off the fact... I really want to work off something that says these ones are congruent right here. I have sets of congruent angles here, and then those would be congruent because they're linear pairs from this guy, if that makes sense. So by definition of a parallelogram, I can have a set of opposite sides congruent and opposite angles congruent, and then a linear pair would state those other angles to be congruent, and then they'd be congruent by angle side. So let's work that out. So because JKL, and I'm sorry that I'm typing this stuff, so I'm losing out some of the formatting, but because JKLM is a parallelogram, then JM is equal to KL. I should say LK. LK by the parallelogram or opposite sides congruent theorem. Okay, so there's the start. And I can't just call them angle J and angle L. Angle KJM and angle KJM MLK are congruent by the opposite angles congruent theorem. These aren't converses. These are just the theorems themselves. The linear pair, is it called a postulate? The linear pair postulate would then show that angle GJM is equal to or congruent to angle HLK. So the ones that I marked with single marks are the ones that I'm getting at. Therefore, triangle, sorry about this, MGJ is congruent to triangle KHL. I probably shouldn't have typed this apart. By angle side congruence. Now, because that last one does have a congruence thing, I feel like I got to make up for everything else that doesn't have it. Congruent, congruent, congruent. I should probably put triangle symbols all over this kind of dumb thing. Congruent, segment bars, all that kind of stuff. So, listen. These two sides are congruent to each other because this is a parallelogram. Opposite sides will be congruent. Boom, we got those. All right, those are within those triangles here and here. Next thing, opposite angles are congruent. This one and this one in this parallelogram. Because those are two congruent, those two are congruent to each other, because these make linear pairs with those congruent angles, those linear pairs are congruent together. A transitivity property, linear pair postulate will make that stuff happen, kind of connecting those. Now I have an angle side case, angle side case. Those two triangles are congruent. All right, number 39. And it looks like we're doing a bunch of these now proofs. I wonder if two column proofs are the way. We'll figure it out. So we're trying to prove now the converse of the parallelogram angles congruency converse thing, whatever you call it. So number 39. Given these are here, prove that this is a parallelogram. I'm guessing we're working off of the drawing a diagonal kind of concept with this thing. Trying to decide if that's the way. Like, we can either do that, or we could work off of... You know what else we could do? We could probably... So, they never brought up the same side interior angles thing that I kept bringing up. I feel like we can go without the diagonals if we do that. Because if we show that we have sets of same side interior angles, then we could say that lines are parallel that way. So let's do this instead. I'm going to bring up just some basic thing that's going to say, all right, I got congruent angles here, congruent angles here. We know that all of them add up to 360, things like that. So any two of them would add to 180. And then ones that add to 180 are supplementary, and then the linear pair thing. Same side interior angles would have parallel lines. So I think working off that would be a little bit cleaner, because I won't have to draw diagonals to split something that's not even split into two congruent parts. So let's go off that. Let's try statements, reasons. This is just the first proof. So I think this is where we're hitting all those proofs of those theorems, and they're leaving it up to us to do it. Statements, reasons. So first, we're given angle A congruent to angle C, and angle B congruent to angle D. Step 2, so congruency. So they're equal to each other. Measure of A. Do I need to use that yet? Measure of angle A equals measure of angle C. Measure of angle B equals measure of angle D. That's the definition of congruence. Congruent angles means equal measures. So if you add all four of these, you get 360, right? Measure of angle A plus measure of angle B plus measure of angle C plus measure of angle D equals 360 degrees. This is a polygon angle sum theorem. polygon, I don't know its official name, polygon angle sum theorem for a quadrilateral, right? Quadrilaterals, angles add to 360. Now, the reason why I brought this A equal to C and B equal to D thing is now I can do a substitution. I could put in, like, A for C's measure, right? Measure of angle A plus measure of angle B plus measure of angle A, and then I could put B in for D. Measure of angle B equals 360. Sorry about that. I'm really running out of room there. This is by the by substitution. I want to kind of put variables in their place. I could probably just put A and B and stuff like that. So now 2 times the measure of angle A plus 2 times measure of angle B is 360. I simplified. And now 6, if I divide everything by 2, measure of angle A plus measure of angle B is 180. That's a division property of equality. Division prop poop of EQ. So A and B equal 180. Boom. I just said these two add to 180. Okay. Now I could probably do substitutions off this, so keep this one in mind. We can do that probably several times. We need at least one more time for it. So measure of angle A and B are 180. Should I just say this one off of it, supplementary? Then I can copy and paste all those. Angle A and angle B are supplementary. That's definition of supplementary angles. Okay. They are also same side interior angles. We're showing the consecutive angles being supplementary, supplementary for this to work. But it's not a converse. They never still quite stated that it was a converse of that thing. I think that would make sense, though. Did they have one? Did they have one that said a consecutive interior angles converse or no? Because that has to be one. That's what I'm building this thing off of completely. We're going off the things here. All right, number 8. Now we have the parallel lines. That would be BC. I'm looking at my other thing. BC parallel to AD. So I'm looking at the page on the 30 end. BC would be parallel to then AD by the converse of the same side interior angles theorem. And now I have one set of parallel lines. Oh, okay, then that's fine. Then I can just say that. I can say those are parallel. Boom. Or, as I was looking over here, boom. Now let's do the same thing, but with, and I don't have to do much. I'm just going to go based off the last 3 sets here. Although apparently it copied more than I wanted it to. Let's get rid of that. And I'm just going to change some letters around now. Now I just need to do another substitution. Change these numbers into 9, 10, and 11. And then have a statement 12 say it's a parallelogram. Not now I just. It's kind of a long thing. But, yeah, working off of it. So this isn't going to be division property of equality anymore, though. It's going to be a substitution. Or transitive property, if you will. Do I just want C and D? Measure, no. Now I want like B and C. So A is going to turn back to C. Let's turn this back to C by substitution. By the way, substitution means substitution property of equality. And then now C and B are supplementary because they add to 180. And now the other 2 sets of lines are going to be parallel to each other. So this is statement 10 and 11, 10 and 11. So C and B are supplementary. That makes AB parallel to CD. So now these 2 are parallel here by that converse. Now it's a parallelogram by definition of parallelogram. Okay. I think I did what I needed to there. Cool. All right. That is number something. All I know is I still have 2 more proofs to go after that. That's number 39. 11 more questions and at least 2 more proofs. Whatever knocks on the other side of this door, I have no idea. Obviously, critical thinking and open-ended and how do you see it? All right, proving a theorem. Use a diagram of PQRS with the auxiliary line segment drawn to prove the opposite sides parallel and congruent theorem. So this one's already kind of drawn for you. Oh, that didn't go as low as last time, though. Okay, so this is that other theorem there. So, okay, I'll leave the drawing over there. Let's go statements and reasons straight up. What's my handwriting? I want to feel like I want to rush this entire thing. I'm just not. I'm not saying I'm not into it, but I've felt the time constraint against me on this one. And I'm like, yeah, let's go. Let's get it done. So we got QR parallel to PS. And then QR congruent to PS. All right, given and marked, by the way. There's also the auxiliary line. I don't know if I'm supposed to say anything about that. I don't know if that matters. Okay, if I have... So, okay, this one's going to be a lot quick. Well, I don't know what I have to do to prove opposite sides equal. Okay, I'm going to basically go alternate interior angles here, reflexive property here, 2 sets of congruent triangles. Then these are congruent by the thingy, by CPCTC. And then lastly, now it's congruent by the opposite sides congruent converse. Parallelogram, opposite sides converse. I think we can use that because that one's already been proved. So I think that's going to be pretty fast. So statement 2, listen, the line's already drawn. So now I'm going to say angle RQS. Angle RQS is congruent to angle PSQ. By the alternate interior angles theorem, we have parallel lines, so we can use that for those 2 specific ones. Statement 3 is, I'm having multiple of the same marks, but statement 3 is going to be this one, QS congruent to itself, or to SQ. QS congruent to SQ by the reflexive property of congruence. Now the triangles can be congruent by side, angle, side. Remember the initial ones we already had here, QR and PS. So I can now say triangle, this is a CPCTC one, triangle PQS is congruent to triangle RSQ by side, angle, side. And then I want to now say PQ congruent to RS right there. Or I want actual corresponding parts. So PQ congruent to, RS. PQ congruent to RS by CPCTC. And now we can say it's a parallelogram, not by definition. PQRS is a parallelogram. Because I said so. Because the parallelogram opposite sides converse. Now that both sets of opposite sides are congruent, we already proved that, we can use that. I guess, right? That's how I'm going to work that. Okay, cool. All right, number 41. 10 more questions. How long have we gone? I don't even know where my clip thing is. An hour and a half? Let's see if we can finish at the 2-hour mark. Number 41. Oh, that didn't go that low. Prove the parallelogram diagonals converse. So now we're getting to this guy. I mean, this can go really fast. Do I have to do 2 sets of congruent triangles in the opposite sides thing? Maybe. I can do... Sorry, I'm looking into ways I can do this faster or slower, all depending on what we have. No, I don't have to do 2 sets of congruent triangles. Okay, so here we go. Now that we proved the last one, we can use this one. I'm going to use this. Well, that's not a converse. Oh, no. I take it back. This isn't a converse. I can use this one now, and I will at the end. I'll show you. I'm excited. Let's kind of copy and paste and delete everything that's not statements and reasons. Excuse me. I don't know why I felt to go this way about it, but I did. Wondrous. Okay, I could have... Here we go. Given The diagonals bisect each other. Oh, they didn't even have the courtesy to just tell me that they're already congruent. All right. Diagonals JL and KM bisect each other. All right. Normally, we would make the markings for ourselves, but they're already made for us. That's why I thought that would be our given. So now I got to say KP is congruent to MP. Segment KP is congruent to segment MP. And JP is congruent to LP. This is definition of segment bisectors. Definition of segment bisectors. All right. So now we have all of those congruent marks. Okay, I can use a pretty simple one here, vertical angles. I got vertical angles here and here that can be shown to be congruent. So angle KPJ, angle KPJ is congruent to KPJ, MPL by the vertical angles theorem. That's vertical angles theorem. Now I have congruent triangles here. I have this guy, KPJ, congruent to MPL as triangles as a whole by side angle side. Triangle KPJ is congruent to triangle MPL by side angle side congruence theorem. Okay, here's what I'm going to do. Now I have the congruent triangles. I'm going to be able to show these are congruent to each other by CPCTC, but I want to make another statement after that, and I'll show you what it is. But let's start with that one. Segment KJ is congruent to segment LM by CPCTC, but I'm going to use another one. I have other corresponding parts such as these two, like this one here and this one here, and it doesn't technically matter which ones I find as long as they correspond. K does correspond to M. Got to use two arcs though. K does correspond to M in that sort of way, but now that I have these angles congruent, they're alternate interior angles that can make these lines parallel. So at the same token of this by CPCTC, I also have angle JKP congruent to angle LMP by CPCTC. I could have maybe used those on the same line. CPCTCC. And then that makes those sides parallel. JK parallel to LM by the converse of the alternate interior angles theorem. JK is going to be parallel to LM by the converse of alternate interior angle theorem. So now that is parallel to that. Now I have opposite sides that are both parallel and congruent, and that'll use that opposite sides parallel and congruent theorem, which I can use because we now proved it, right? It's only within the scope of the problem we can do something like that. So finally, statement 8, JKLM is a parallelogram. By the opposite sides parallel and congruent theorem. So parallel and congruent theorem. Okay, 8 steps for that one. Not bad. No more proofs. Number 42. Write a proof. DEBF is a parallelogram. AE equals CF. Prove ABCD is a parallelogram. AE equals CF. So these are the same. It says they're equal in length. It doesn't say they're congruent. Parallelogram. That means these are equal. Therefore, boom, boom, boom. I can use segment addition postulate, which then says those are the same. Okay, I'm good there. Sorry, I'm working out my proof before I prove. Is there a way to show these are can we say for sure these are collinear? Because if so, these are parallel. These are parallel here, and then I'd have, those aren't alternate interior angles. Those are just angles. But these are opposite congruent angles, and then those would be congruent here. I don't care about that though. Let's see. If these are parallel, sorry, I'm building it before I actually go to it. I see what I want for the, oh, these are already parallel here. Duh. All right, let's go through it. I'm sorry. We're good. Okay, segment addition postulate will show these two are equal to each other. These are already parallel by definition of parallelogram. Okay, we got it. Okay, let's go to war. Got it. Okay, statements, reasons. The big ol' S, the big ol' R. All right, number one, DEBF is a parallelogram. I was going to say true, given. There is the AE equal to CF. I'm going to wait on that for one moment. Two. Here's the thing. I actually like that they say AE equals CF. I don't care that they're congruent. I care that they're equal. I'm going to use math numbers more so than the congruence parts. So they actually help me with that. Now, DF, I'm going to mark some things on here in a bit as well. But DF, segment DF is not only parallel to BE, segment BE, but they're also congruent. Because, well, those are two different reasons. Let me do that again. These are parallel by definition of parallelogram. And these are congruent by the parallelogram opposite sides congruent theorem. I keep forgetting the name. I'm just going to call it that. Opposite sides congruent theorem. It works out. Opposite sides of a parallelogram are congruent. So let's mark those things up. So I got opposite sides parallel, but I also have DF congruent to EB. Now, if DF is congruent to EB as segments, that means their lengths are equal, and you do need that part. DF equals BE by definition of congruence. Now, I have trouble with this part here. In that if I add these... Oh, I'm sorry. No, this is fine. I'm sure I can use this. But F, now here's the other given. AE equals CF is given. Now I'm going to use... I think I can just say... Hold on. DF plus AE... No, AE. DF plus CF, or FC, equals DC. That's segment addition postulate. And BE plus EA equals AB. I'm saying all the letters very wrong. BA. That's segment addition postulate. But I want to say that those things are equal. I guess that's the transitivity property of equality, I think. Segment addition postulate. I think I can use transitive property of equality for this next one to say DC equals BA. DC equals BA. So I added two things that are equal, DF and BE, with two things that are equal, FC and EA, to make two things that are now equal. I think that can work that way. Two equal things added to two equal things equals two equal things. Transitive property of equality. I think that works. If you have equal opposite sides here, boom, and boom, then they also make congruent segments. Once again, definition of congruence. I'm 2 steps away. Segment DC is congruent to segment BA by definition of congruence. And lastly, that makes it a parallelogram because the opposite sides are already parallel. We know that. Is that allowed for me to I don't have to say DC parallel to BA? Is that good that I can still, they're still part of the collinear parts? It's still parallel. I think that is fine. If I had to say anything with DC parallel, I don't think I have to. So we'll say ABCD is a parallelogram. by that opposite sides parallel and congruent theorem. It's the same one as before. Opposite sides. I'm glad we know that one. Parallel and congruent theorem. Okay. All right, that's number 42. Number 43. Three interior angle measures of a quadrilateral are 67, 67, and 113. Is this enough information to conclude the quadrilateral parallelograms? Man, explain your reasoning. No. They're pretty close to that idea because you're thinking, well, the last angle has to be 113, so it must be. But there are two different cases we have, right? There's one case that would be this, 67, 67, 113, and yes, the last one would indeed be 360 minus. I'm doing this just straight up, just the concept of what the last angle would have to be in the quadrilateral. 360 minus I don't know what those add up to. Well, 180, so 247. 247 is 113. So this would have to be 113, but that's not the only drawing you gotta make. It says three interior angles of a quadrilateral. That's a case where it could be, but it could also be this. Okay, this could be your 67, 67, 113, 113. Now, once again, we haven't dived into trapezoids at all yet, but this is a trapezoid. It's I think it's an isosceles trapezoid. No, never mind. Yeah, I think it's an isosceles trapezoid. So, no, not necessarily. No, because consecutive angles could be congruent. One set of pairs instead of opposite angles, basically. In a parallelogram, opposite angles are congruent, not consecutive. So there's one chance that it could be, one set that it's not. All right, number 44. Much better than proof. Here's the how do you see it. A music stand can be folded up as shown. Trying to think what a music stand is. I didn't know you could fold them up. In the diagrams, AE, FD, and EBCF are parallelograms. Which labeled segments remain parallel as the stand is folded? They're not asking us to explain why. So there are different sets here, and they don't have the internal ones. So, okay, as it's folded, which remain parallel, just these ones would remain parallel. So, okay. Yeah, I'm not going to do much more with that. Just asking how you see it, and that's how I see it. So AD would remain parallel. That's not parallel. Would remain parallel to EF, which would remain parallel to segment BC. They kind of fold up together, and they're separate things of space. Yeah. Now, if it folds all the way upward and they touch each other, I don't know if that counts as parallel or not anymore. All right, 45, critical thinking. In the diagram, ABCD is a parallelogram. That's in black. BF and DE are both 12. Okay, there's a lot of... I'm trying to label this. Let me enlarge this guy. And see what I can do off it. Ooh, it's pretty enlarged there. So BF... Oh, BF is the little guy. BF and DE are both 12. Yeah, enlarge that. So 12 and 12, like that. We got a parallelogram, remember that? And CF is 8. Or CF. That? 8? Find AE. Explain your reasoning. So I have a parallelogram, which means parallel, which means parallel, congruent, opposite angles are congruent, diagonals bisect each other. This thing inside, must be a way of saying this thing inside is also a parallelogram. It says find AE, explain the reasoning. I'm guessing it's going to be 8, but I want to see what I can do to work off that. Well, we can say this. Oh. We couldn't say that. Oh, we could. Oh. I have side. But I don't know AE yet. There's something in here that should force me to say that because those are both 12, I'm within... I'm trying to show that these two triangles are congruent, basically. I think that there's got to be enough there somewhere to do that. I don't want to use the 12s and just say, therefore, this must be a parallelogram. Something inside here must require that. In fact, I don't think there's something that requires that, but except for those, opposite angles and sides are parallel, diagonals bisect each other, and the angles are congruent with each other. This is congruent to this, and that's good information within them. I need to find a way to say that either that's congruent to that, which I don't see anything that would do that. That's congruent to... Oh, no, that's an angle side case. No, it's not. No, it's not. Ignore the 8. Ignore the 8 for a second. All right, this is congruent to this by alternate interior angles, and then I have that a side angle side case with a side angle side case. Therefore, by CP/CTC, AE would be the same as that. So, do I have to explain my reasoning? So, angle ADE is congruent to angle CBF by alternate interior angle theorem. The parallel lines would make it so, given that it's a parallelogram, because segment AD is congruent to segment ADCB, and if those lengths are the same, then I'll just say that. So DE is congruent to BF. It's not a full proof, just as explained. Then triangle ADE is congruent to triangle CBF by side angle side. So AE is congruent to CF by CP/CTC. Therefore, AE equals 8. I actually use green. Okay. So they're going to be the same, therefore they're equal. That kind of thing. I know I skipped some steps that I wouldn't have in a proof, but there's that. All right, create a regular hexagon using congruent parallelograms. Number 46. Can they overlap? I don't know if I can do it with or without overlapping. Just asking if they can. If I have congruent parallelograms, create a regular hexagon. So just for good measure, here is a regular hexagon in and of itself. There's the tool. Let's see what kinds of regular parallelograms we could do. And I don't know if I can actually draw it within and make it work like that. So, okay, clearly I can't make my own parallelogram of that sort. What I could do is congruent parallelograms. I guess you could do the overlapping. So I'm going to do 2 sets that are like that and then overlap them so that I have, because this is not congruent to those, I would have another set that would just overlap in this direction. I wonder if that's allowed. So let's try this. I'm going to make one parallelogram, and I'll just keep copying and pasting it. Oh, it's got to be a regular hexagon? Ooh. Ooh. I can't guarantee anything I make will be regular outside of the regular hexagon I already made. So I'm going to make the hexagon first and then design around it. So with this, I'm going to try... Gosh, let's see. Let's do this and bring this piece over just to give me my shape. Like that. So here is a parallelogram that I have, sort of. 1, 2, 3, 4. And then let's see if we can go off of that. I don't know if that's the right thing they're talking about, because I could just, again, 1, 2, 3, 4. Group it. Copy, paste. Okay, so I have that one. Let's flip it over this way, left, right, and then go right there. And then kind of just do the same thing. Copy, paste, copy, paste. Copy, paste. And copy, paste the first guy. I don't know if that counts for what they want, but without my hexagon shape, I made the hexagon. That's my go-to. Now, I already had the tool, but if you think about what's needed, I can't think of another way to do it when it comes to parallelograms, because parallelograms need those sides to... I like that one. There's overlap, but I like that one. I think that's what I'm doing there. So that's number 46 for me. I know I had the regular hexagon first because I didn't know how to measure it to scale with that. All right, 4 more. The parallelogram consecutive angles theorem states that the quadrilaterals of parallelograms consecutive angles are supplementary. Write the converse of this theorem. I knew there was a converse. I forget if I didn't do that before. Write a plan for proving the converse, include a diagram. I already did that, though. Didn't I? Okay, so number 47. So the consecutive angle is a quadrilateral. Okay, write the converse. All right. Converse. If a quadrilateral, because this is the one I was stating what has to be one. If a quadrilateral has consecutive supplementary angles, has all consecutive angles supplementary, I guess, then it is a parallelogram. Like all sets of them, the consecutive ones. Okay, so if that's my converse, it says write a plan for proving it, including a diagram. So here's my parallelogram. I got some x's and y's and stuff. I'm going to use x's and y's that are supplementary. But I don't know. I'm still going to call it A, B, C, D for now and see what I want to do with that. We know they're all supplementary. I feel like that was this proof here. This one... I feel like that was this one right here. I went based off of the... Well, this talked about them being congruent, but I got to that part. And then I worked it out from there. It was the same side interior angles thing. I really just wanted to go off the same side interior angle stuff. So my plan is the same side interior angles bit. The plan is to show any sets of angles that are supplementary would create parallel lines by the converse of the same side interior angles theorem. So by definition, the quadrilateral would be a parallelogram. Yeah, so I don't know if that kind of works. It seems to. That's how I'm kind of stating it. So yeah, you know, if these two are supplementary, if x plus y, whatever, or a plus b adds to 180, boom, right here. If these are that would make these things parallel by the converse of the same side interior angles theorem right there. And then same thing, b plus c. This is exactly what I did on the other one. If b plus c is 180, boom, then that would make these lines parallel by the converse there, and then by definition it's a parallelogram. That's my plan. That's the way I would go for it. All right, number 48 is a proof. Before I see number 50, I don't want to be sad. Looks like it's not a proof. So 48 is my last proof here. ABCD is a parallelogram. Angle A is a right angle. Prove B, C, and D are right angles. Okay, this one seems pretty straightforward. I just don't know how much I have to write, translating from measures of angles to all that kind of stuff. Let's see. So for number 48, I have my reasons as well as I have my statements. I'm not finishing within the 2 hours, am I? I don't think so. All right. Given it's a parallelogram, is a parallelogram, and angle A is a right angle, Okay, so those are given. So what can we do off of that? Okay. Angle A and angle C would be congruent because now there's more I'd have to state to that, right? But angle A is congruent to angle C, not by definition of a parallelogram. The opposite angles theorem, parallelogram, um, opposite angles congruent theorem. I believe that's the name. So A is congruent to C. Now, A and D would be supplementary and all that kind of stuff. I'll prove that they're all right angles. So angle C is a right angle. Because right angles congruent to other angles are also right angles. I'll just call it right angles theorem. I feel like I'm supposed to say more with that. No, it's a right angle, therefore it's congruent. Ooh. Okay, let me do this. I'm going to move these down a little bit. Okay, I'm going to get rid of this line here. I'm going to do something that will apply and help me with some of the other angles later. A is congruent to C, that's fine, but not yet as far as statement goes. Let's start. If angle A is a right angle, that means the measure of its angle is 90 degrees. This will apply later when I get to do them with B and D, I think. So that's the definition of a right angle. Now that A is congruent to C, I can say measure of angle A equals measure of angle C. By definition of congruence, I might be over speaking on these things here. Basically what I'm doing is I'm going to say these two are congruent to each other. They're both 90 degrees. These are supplementary to each other, and one's already 90 degrees. And it just kind of works itself out from there. Measure of angle A equals measure of angle C, definition of congruence. But I might be overstating the steps, basically. Because everything I said out loud was basically it. So measure of angle C is 90 degrees by the transitivity property of congruence. Of equality. Sorry. Therefore, angle C is a right angle. I'll do that with all the other ones, but angle C is a right angle there. Okay, D. A and D are supplementary. By the consecutive interior angles theorem. And same with angle B. Maybe I could just do it with C. Ugh, it's just a lot. It's a lot that I'm stating here. How about this? Let's do C as a right angle now. By definition of right angle. Again, I'm probably doing more than I need. Then I'll say A and B are supplementary, and then I'll say C and D are supplementary. I'll just use them both in the same lines. Angle C and angle D are supplementary. So same reason. So I get to do all these together now. That's statement 7, though, not statement 6. Statement 7. All right, statement 8. They're supplementary. That means they add to 180. And I already have their measures as like 90 and stuff, right? So I can say, this is why I'm going to keep them separate. Measure of angle A plus measure of angle B equals 180. Definition of supplementary angles. Measure of angle C plus measure of angle D equals 180. Def of supplementary angles. I feel like there's probably another theorem. See, there are a lot of theorems I don't know the name of or which ones I can use in scope. But an angle supplementary to a right angle is also a right angle. It's basically all I want to say. Now I'm going to substitute 90 for both A and C because we already know that they already equal that. 90 plus measure of angle D equals Plus 180. So again, same lines for both causes. Substitution. Sorry, the handwriting ain't good. Number 10. Again, everything I'm stating is the most complete version of it. There are theorems that they probably say that bypass all this to make it like a 5-step thing instead of like a 13-step thing. So measure of angle B, if I subtract 90 from both sides, I get 90. Measure of angle D is 90. By subtraction property of equality. And then 11, because they're 90 degrees, angle B and angle D are right angles. We already said angle C was back one. So now we know those are also right angles. That was a long way of stating that congruent 90-degree angles, or congruent, an angle congruent to a right angle is a right angle, and an angle supplementary to a right angle is also a right angle. That's pretty much all I said for all those things. That's the concept. It's because of the fact that opposite angles in a parallelogram are congruent and consecutive angles in a parallelogram are supplementary. That was kind of why. So anyway, what was I saying? Definition of right angles. The definition of right angles is they measure to 90 degrees. So 90-degree ones are that. There. Okay, long way of putting that. Probably could have found a more sufficient way of doing it. Number 49. The midpoints of the sides of a quadrilateral have been joined to form what looks like a parallelogram. Ooh, maybe. Show that the quadrilateral formed by connecting the midpoints of the sides of any quadrilateral is always a parallelogram. I think I did this once way back when. Draw a diagram, include a diagonal of the larger quadrilateral. Show how two sides of the smaller quadrilateral relate to the diagonal. Pardon me. I almost feel like they want to do a coordinate proof with this one. Okay, let's do, because I want to pronounce this one less, so I'll make it thinner. So let's do this guy here. They kind of obtuse this thing outward just a little bit. Or protrude it out, I should say. Okay, like that. And then let's go ahead and connect that guy right there. Okay. So just a funky looking quadrilateral. You have some midpoints. I have a midpoint here, and a midpoint here, and a midpoint here, and a midpoint here. Now within there, we made some sort of object. That object might be a parallelogram. Now why? I'm curious. Why? I've seen this on like graphs, but I'm trying to think what we can talk about here. Hint, draw a diagram, include a diagonal of the larger quadrilateral. Show how two sides of the smaller quadrilateral relate to the diagonal. Draw a diagonal of the larger quadrilateral. They must be parallel. So, mid-segments. So, this, take a look at this right here in green. Apparently dotted green. Let's take a look at this in solid green. This triangle, made from the diagonal, this triangle has a mid-segment. This mid-segment is parallel to that guy. Well, this triangle also has a mid-segment, and this mid-segment is parallel to that guy. So those would be parallel to each other. They show that it is by doing that. Okay, so when drawing, so I'm just going to kind of explain it. When drawing a diagonal across the quadrilateral, it creates two triangles with mid-segments as the sides of the, did they already say midpoints of the sides of the quadrilateral for what looks like a parallelogram of the smaller quadrilateral? Mid-segments are parallel to those third sides, such as this diagonal. Two sides parallel, two lines parallel to a line are parallel to each other. You can do this with any sides and any new diagonals. and therefore it would be a parallelogram. Or all pairs, or both pairs of opposite sides would be parallel, making this a parallelogram. So that's cool. I didn't know that. I imagine I could have done this more with coordinate geometry, but I think then it's like it's any quadrilateral, so it's kind of tough. So basically, again, this thing would be the third side of a triangle where this is a mid-segment that's parallel to this thing. But this would also be a mid-segment in this guy that's parallel to this thing. So they're all parallel to each other, which means those are. And then I could do the same thing over here, where I could make myself another diagonal with this one. And then boom, suddenly I have a mid-segment here that's parallel to this guy. And then this mid-segment here is parallel to that guy, so those are both parallel to each other. Therefore, we do have a parallelogram. That does work. Good question. All right, last question, number 50, critical thinking. Show that if ABCD is a parallelogram with its diagonals intersecting at E, then you can connect the midpoints of F, G, H, and J. Okay, so those are midpoints of segments A, E, B, E, C, E, D, E to form another parallelogram. Would this not be another mid-segment thing? I think this would just be another mid-segment thing. So so they're saying that these are midpoints. Like this is a midpoint of this segment. This is a midpoint of this segment. Therefore, this is a mid-segment here, which is parallel to that guy. It's kind of the same question as the other one. I mean, it's a different way that it's shown. But it's just another triangle mid-segment thing. It really doesn't change how that thing works. Show that if it is, you can connect the midpoints there respectively to form another parallelogram. I mean, it's the same bits. This one's maybe more confusing looking because I didn't thicken. One's a different thickness than the other. But number 50, I'd say it's more the same thing. Show that if it is, then you can connect them. Because the mid-segments... Wait, do they call them mid-segments? The diagonals. Excuse me. You can connect the midpoints. The connected midpoints of the segments made by diagonals are now mid-segments, which would be parallel to sides that are already parallel to each other. This would maintain the parallelogram shape. I think that the previous problem really helped us see what this thing was even more so with a different kind of connections, a different kind of way that it's drawn, but it still works itself out in the same kind of way. I'm going to go with that for the mid-segment bits because that's how mid-segments work. Mid-segments are parallel to their third side there. All right, guys, that'll do it for this one. This is Mr. Robinson. Thank you so much for watching. My mysterious chair thing has come and gone. It has helped itself, hurt itself, but there's that. Next, we would have the 7.1 to 7.3 quiz. We're hopefully a little less on the proofs and stuff and just more doing on hard application. All right, guys, take care. I will see you in the next one.